Thank you, Manjusree, for giving a very good welcome for me. And at the outset, let me thank IWSA for inviting me to this. And actually, I feel it is an honor for me to be present in front of so many senior scientists and even junior scientists who have made significant contributions. And definitely, this space technology has got numerable applications right from Earth, low Earth to the galaxy. It has got numerous applications and even societal applications also it has got. And it is also very close to my subject as it is a very challenging and interesting field. Now, I would like to invite the first speaker, Hashima Hasan. I think that she has joined the online. She is the NASA program scientist for NSTAR and she is a Deepti program scientist for the James Webb Telescope. And I think many of you may be aware of James Webb Telescope, which has done significant contribution in almost all fields of the astronomy. And it has not only explored our planets, like solar system planets, it is even exploring the planets of other stars in our galaxy. And it is also giving a light on how the universe is formed. Definitely, she will be able to throw more light on that because she has published many articles in various peer-reviewed journals like astrophysical journals. All these things are even related to Hubble telescope also. And in her role as a program scientist, she make sure that each project missions remain possible and true to NASA strategic objectives. She has been program scientist for many other missions also, such as the Wide Field Infrared Survey Explorer, Gravity, and Extreme Magnetism, Stratospheric Observatory for Infrared Astronomy, Hubble Space Telescope, Explorer Program. Many she has done. Definitely, you will know more about this because we will not be aware of so many projects that work. What are the major contributions from those projects? She will explain. She and coming to her qualification, she has received a doctorate from the University from Oxford, UK till 1985. Dr. Hasan conducted postdoctoral research and held teaching positions in the areas of theoretical nuclear physics and in environmental science. She was the optical telescope assembly scientist for Space Telescope Science Institute, Baltimore till 1994. When she joined NASA headquarters, she received certification for the Senior Executive Service in 2004. She has published articles in, already told, in many peer-reviewed journals and publications of the Astronomical Society of the Pacific. She has been honored with prestigious awards and fellowships throughout her outstanding career, including the NASA headquarters. Exceptional Performance Award in 2008, the National Research Council Resident Research Associate from 1981 to 1983. Commonwealth Fellowship also she got from 1973 to 76 and received a gold medal for physics and merit award as a student. This is really, actually, I'm very feel proud and also I feel honored to introduce her who has got so many qualifications, who has worked in so many important missions. Now let us listen from her. Okay. Thank you. Hashima Hasan.
Yes, good evening, namaskar. It's an honor and a pleasure to be here today to share with you some of the early results of the James Webb Space Telescope. So if I may share my screen, I have a few slides. How do I share the screen? Okay. There. Can you see my slides? Can you see my slides?
Yeah, madam, visible.
Okay. Webb is a technological wonder with its 6.5-meter primary mirror and a tennis court size sun shield and 4 powerful instruments. It is already unlocking some of the secrets of the early universe. Launched on December 25, 2021 on a French rocket from the European Space Agency spaceport in Kourou.
And we have engine start. And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So Webb was placed in an orbit 1 million miles from the Earth at a Lagrange point 2. After 6 months of commissioning, President Biden unveiled the first image shown here on the right. It's a view of the galaxy SMACS 0723, as it appeared 4.6 billion years ago, with many more galaxies in the front and behind the cluster. And this was taken by the near-infrared camera NearCam. On the left-hand side is the same field taken with the mid-infrared, where you can see the details of the dust. The blue galaxies show the stars with very little dust, and the red ones are shrouded in dust, and the green ones are showing hydrocarbons and chemicals in those galaxies. Here is another galaxy field with the acronym JADES, which was released on June 25. And there are greater than 45,000 galaxies here, and 700 galaxies have been identified or as good candidates that they existed when the universe was between 300 to 500 million years old, and they contain a multitude of hot young stars. So we are really looking back in time to within 1 billion years after the Big Bang, when viewing the youngest of these galaxies. As the light left these first stars at galaxies in the blue and ultraviolet, it started stretching as the universe expanded, and it has now reached the infrared. And what Webb observes, it's optimized to infrared so that can see the first stars and galaxies. Webb is also has spectrometers, because spectra provide an incredible amount of information, as demonstrated in this image of Hubble Space Telescope. A strip across the Southern Crab Nebula shows the elements which this nebula contains. So not only are we able to get the chemical composition from spectra, but astronomers are also able to measure the speeds and distances and ages of astronomical objects by studying the spectra. Let's quickly look at the timeline of the universe. It started when the entire mass and energy of the universe was scrunched into a small point called the singularity, which suddenly started expanding in a phenomenon the astronomers have called the Big Bang. And then neutral hydrogen was formed, and that period is called the Dark Ages. And then it clumped together with gravity, and nuclear reactions started taking place, and stars were born. And the heat from the star started re-ionizing the neutral hydrogen, a period known as re-ionization, till the universe was transparent. And this period from 200 to 400 million years after the Big Bang is the key area that Webb is examining. So here's an example of what we learned from the Webb deep field. See this little rectangle on the left side in the inset, it's blown up on the right side. It's a galaxy which has been called the Sparkler Galaxy. Not only does it have a peculiar shape, but the astronomers were excited by these little yellow dots around it. And at least 5 of them have now been identified as globular clusters. this the green rectangle, which is blown up at the bottom, shows one of these globular clusters, which are collections of ancient stars that date back to a galaxy's infancy. So they can contain clues about the early stages of galactic formation, growth, and evolution. These could be some of the oldest globular clusters ever seen, perhaps dating back to the time when the universe first began to birth stars. And there's a wealth of information in this deep field where the astronomers will be mining for a long time. Here is a result from one of the JADE's fields, which shows a new frontier for redshift frontier, which means how far back we can see in time. So about 250 galaxies were identified going back to a time when the universe was less than 500 million years old, and at least 4 of them have been identified to be within 350 million years of the Big Bang. And these have been identified by a technique called the Lyman break, which is a characteristic wavelength and below which light is absorbed by the neutral hydrogen. And by identifying how far this wavelength has moved along the spectrum, we can identify when these galaxies existed. We also get a lot of information on galaxy formation by looking at the impacts of galaxies. And here is a nearby galaxy called the Cartwheel Galaxy, which was impacted by the galaxy on the left, which went right through the Cartwheel Galaxy. And the direct impact is a lab for star formation. The galaxy displays many individual blue dots, which are individual stars or pockets of star formation. This image here is a superposition of images of the taken with the near cam in the near infrared and the mid infrared. The near infrared image reveals the difference between the smooth distribution of the shape of the older star populations and the dense dust in the core compared to clumpy shapes associated with the younger star population outside of it. The mid-infrared image reveals regions within the Cartwheel galaxies which are rich in hydrocarbons and other chemical compounds, as well as silicate dust, like much of the dust on Earth. And these are colored red in the image. Here's the image of another galaxy, also called the Phantom Galaxy. And the Webb's sharp image has revealed delicate filaments of gas and dust in the grandiose spiral arms, which wind outwards from the center of this image. A lack of gas in the nuclear region also provides an unobscured view of the nuclear star cluster at this galaxy's center. Webb gazed into this galaxy with its mid-infrared instrument in order to learn more about the earliest phases of star formation in the local universe. The addition of crystal clear Webb observations at longer wavelengths will allow astronomers to pinpoint star-forming regions in the galaxies, accurately measure the masses and ages of star clusters, and gain insight into the nature of the small grains of dust drifting into interstellar space. Another set of interacting galaxies is the Stephan's Quintet, which shows details on how interacting galaxies trigger star formation in each other and how gas in these galaxies are distributed. Tight groups like this might have been common in the early universe. So by studying these, we learn more about galaxy formation. The topmost galaxy here, NGC 7319, harbors a supermassive black hole, which is actively pulling in material and putting out light energy of 40 billion suns. Webb will help scientists understand the rate at which supermassive black holes feed and grow. Webb also sees star-forming regions much more directly, and it is able to examine emissions from the dust at a level of detail impossible to obtain till now. Now let's go into looking at star birth in objects closer to us. And this is a famous Eagle Nebula made famous by Hubble. And here in the infrared, we start seeing new forms, new stars, which were cloaked in dust in invisible image, but infrared removes this veil of dust, and the newly formed stars are the bright red orbs that typically have diffraction spikes and lie outside one of the dusty pillars. The columns are made of cool interstellar gas and dust that appear at times semi-transparent in near-infrared light. The wavy lines at the edges of the pillars are ejections from stars that are still forming within the gas and dust, and the crimson glow comes from the energetic hydrogen molecules that result from jets and shocks. A very exciting result that recently came out of a nearby young star, Fomalhaut. For the first time, we've seen asteroid belts in a star outside our solar system, and these belts are far more complicated than our own simple asteroid belt and Kuiper belt in our own solar system. This belt has, there are 3 rings in this belt, and there's a great dust cloud in the outermost belt, and the astronomers are studying it to try and understand where planets would form along this belt. And now let's look at the death of some stars. Here is the Southern Ring Nebula, taken both in the infrared and in the mid-infrared. The near-infrared image on the left shows details of the clouds of gas and dust which are ejected by the dying star. And the outermost layer are the layers which were ejected first, and the innermost layers are the ones which were ejected later. On the right-hand side is a mid-infrared image, which has for the first time revealed that the second fainter star, which is ejecting the gas and dust, was shrouded with dust, and the 2 stars are orbiting each other and mixing up the gas and dust and ejecting it into interstellar space to go out for a long, long distance and time. Here is an example of another star called a Wolf-Rayet star. And these are evolved massive stars which have lost their external hydrogen layer and are burning helium and heavier elements inside. In this particular star, Wolf-Rayet 124, the nebulous structure is created by material cast off from the aging star, and it is displayed by the glow of the cooler cosmic dust in the mid-infrared. This brilliant stage of mass loss precedes the star's eventual supernova, when a nuclear fusion in its core stops, and the pressure of gravity causes it to collapse on itself and then explode. Webb will help astronomers to explore questions that were previously only left to theory about how much dust stars like this create before exploding in a supernova, and how much of that dust is large enough to survive the blast and go on to serve as the building blocks of future stars, planets, and complex molecules. The image in the right is a cleaned up image of the one on the left, which shows stars with diffraction spikes.
Hashima,
Yes?
you are left with 3 more minutes. You may have to finish your presentation. How many more slides you have?
I have a few more, and I can skip some. If just let me tell me when to stop.
Whichever more important, you can speak about
Yeah,
that.
just tell me when to stop, because I have a lot of examples and I can just stop whenever you want. Okay?
Okay, not required. It is you
Okay.
are the one who can judge which are the slides which are more important for the audience. Afterwards,
Okay.
stop, because you have 3 more minutes. Okay.
Okay, so Cassiopeia A is a supernova remnant, and on the exterior lies curtains of material glowing with warm dust and emission, and the filaments with clumps and knots in the interior is material from the star itself. And there is a green loop inside, which the astronomers don't understand where it came from. Infrared light also helps us to find distant planets, and Webb has already taken its image, direct image, of a distant world, which is really exciting. And Webb has also discovered its first rocky planet. And by taking its spectrum, we see that this planet does not have an atmosphere, because you can see on the right, the spectrum is represented by a dot, it's featureless, whereas the green line would represent a methane spectrum, and the purple line of carbon spectrum. But it has, in fact, found a planet with a rich atmospheric composition containing water, sulfur dioxide, carbon monoxide, sodium, and potassium, as well as signs of clouds and first ever clear evidence of carbon dioxide in a planet outside our solar system. This planet was what is known as a hot Saturn, and it's the first evidence of photochemistry. And so that is really exciting. Webb is also being used to re-examine our own solar system. We've taken an image of Jupiter, where you can see the aurora and the weather on Jupiter, as well as rings and moons. There's a very beautiful view of Mars, where you can see more details, and then a wonderful view of Venus, which shows a lot of rings around it. And there's a polar cap, which appears in the summer and vanishes in the fall, which is a mystery. And there are clouds at the edges of the polar cap and the planet's left limb, which are lightly connected with storm activity. Saturn's moon, Titan, we can track clouds over it. And this is the only moon in our solar system with a dense atmosphere, as well as the only place besides Earth which has liquid water and lakes. So this is another very exciting object to view. And then this is a very recent result where a water plume from Saturn's moon Enceladus has been observed and studied. And it's found that about 30% of the water stays within the torus, and the rest escapes to supply the rest of the Saturnian system of water. And that marks the end of the science. And I wanted to show some of the technology, but I don't think we have time to do that. So I wanted to point out that all the data from Webb is archived in the Mikulski Archive for Space Telescopes. It's public, anyone can analyze the data, and I hope the astronomers in the audience are already analyzing the data, and if they are not, please go and analyze it. And finally, here are some online resources if you want to learn more about Webb. Thank you.
Thank you, Hashima. Now 5 minutes is there for questions. Actually, I would like to ask the first question itself with the permission of audience. See, you were talking about the age of the stars and all that. First of all, I would like to know, because this is a very complex astronomy, which we are not familiar with that, even though we are working in space technology. How do you find the age of the satellite? That is first question. In that one only I have second question. And you told sun is more than 9 billion years after the Big Bang. And I would like to know how long the sun will be there, how many more billion years sun will be there. Just these things I wanted to know.
So measuring the distance is a complex process. We have something called a cosmic ladder. And so first step is to measure something close by, and that you use something called a parallax method. Next you go from that to the next step, and one looks at supernova explosions and measures from that, and so on. And one method which I showed you of the galaxies, where the spectrum, there's a characteristic wavelength, 912 angstroms, below which UV and visible light gets absorbed by neutral hydrogen. So when you look at the spectrum, there'll be a break in the spectrum at 912 angstrom. And if you see where the break that occurs on the spectrum, then you can see how far it has moved, how much the light has stretched. So then you can measure the distance. So I said there's a whole ladder which is used to measure distances. Now, what is the life of the universe? I don't think I have an answer to that.
Life of the sun. How many more million or billion years sun will be surviving before it become a obsolete star? It will burn itself, right? It has some energy inside it and it is burning.
How long our own solar system?
What I
Are you asking?
know is how long sun will be there as a star.
How long can our sun be as a star or any? So because different stars have different lives. The biggest, heaviest stars, which were first formed, they have a very short life. The smallest stars have the longest life. And our star is somewhere in between. I don't remember the top of my head how much, but it's, I would say actually several million years before we go.
Because I heard one theory saying that sun will become very hot in course of time and it will engulf Mercury and it is very difficult to live on the earth. Some theory was there, but it is not yet have any solid proof for that. That's why I asked.
Yeah, so our sun will, when it's ending, it'll, the outer shells will expand and, all the planets will get burnt up, kind of absorbed in the sun before it dies. As I showed you one dying star, the medium-sized star, the first one, which was throwing out its outer layers of gas and dust. And that's what our sun will also do. I mean, it's already, it does it at a small scale now, you see ejections, but it'll, as the nuclear material burns up, it starts throwing out gas and dust.
Okay, thank you, Hashima. Now what to audience?
Hi, Dr. Hashima. This is Lalita Dhareshwar. Yeah, just wanted to ask you, when we say life of this star or that star, that means what is the zero time? Where does it start from? Is it the point at which the Big Bang took place, right? So, time of Big Bang, I mean, I just want to understand what was there. I mean, was it just energy which was concentrated, because matter had not come into the universe. So it was only a form of energy at that time. And also there is my doubt that many people say that this is a circular process. That means, again, it goes back into the Big Bang at much later time. So what makes the entire matter in the universe collapse together to form that singularity from where the Big Bang will start again second time? So this is something which I don't understand.
Yeah, I don't know the answer to question when it'll happen again. And actually, we don't even know the answer of the first one, that how was the singularity formed and what caused it to expand? All we know is that it suddenly started expanding. And when it expanded, then a soup of elementary particles were formed. And that was the timeline I was trying to show, but I didn't have time. So a soup of elementary particles were formed. And then these particles then started combining to form neutral hydrogen. And then the neutral hydrogen then started collapsing under gravity to form clumps. And then as it started condensing, nuclear reactions started taking place in the core. And that's how stars were born. And that's what will happen in all the stars. The nuclear fusion is taking place inside. And once all the nuclear material has been used up, that's when the stars die. So some end up as neutron stars, some end up as black holes, depending on how much mass there was in the beginning.
Any more questions from audience?
Good evening, ma'am. I just wanted to ask two questions. The first question is, with the help of this James Webb Telescope, any significant additional information about black holes we were able to get? If so, what is that? And the second question is, you told about the identification of a new rocky planet. Is water available in that rocky planet? Just wanted to know.
Yeah, so the second question first, because no, there was no water on this. I went.
Yeah, next we have the speaker Deepti, former ISRO chair, professor ISRO Space Technology Cell, Savitri, Pune University. And she'll be talking about the societal applications of space technology. She will bring us from the galaxy to the Earth now, and she will tell us on the Earth what are the uses of the satellite. Regarding Deepti madam, I've already told she is a ISRO chairperson. She has several important positions, like nearly 100 publications in national and international journals. And she has also written 5 articles in books and has 2 patents, and one is pending also. And she has nearly 36 years of experience in the Pune University. She has several awards and honors to her credit. And special award Women Scientist for Popularization of Science from the Department of Biotechnology, Government of India. And she has got Indian National Science Academy Medal for the Young Scientist 1989. She has expertise in genetics, epigenetics, and her research has dealt with environmental affairs and modulations in response to such, which is an important element in life. And I think it goes on because of the time limitation. I think I will slightly make it precise. She has collaborated with DRDO, BARC, MUS, and ISRO in nanometals biotechnology, metagenomics, and microbial oceanography. She has her group has unraveled the microbial flora in relation to oxygen depleted zones in Arabian Sea and Bay of Bengal. We all know how important it is, and she has been developing innovative approaches and has multidisciplinary expertise and have collaborations with JNU, New Delhi, Goa, IISCR, Pune, IGB. The list goes on. So now I will invite Deepti madam to give the application of this satellite technology. Over to Deepti.
Thank you very much. I will start sharing my scene.
Before
Yeah.
your
I think, sorry.
You have 20 minutes for your presentation. And
Sure. Yeah, so I will start, make it full screen. Give me a second. Yeah, so, after a fascinating glimpse of the early universe and the galaxies, I'm going to bring you to something more real life, day-to-day things, which is, we keep thinking about the satellites and rockets, but the technology and the tools and approaches developed out of it have tremendous applications. And I'm going to touch upon a few to give you a glimpse of this. Okay, so let's say that in last 5 decades, ISRO has made really amazing contributions in developing infrastructure, building capacity, having innovative and indigenous technologies, partnered with other countries as and when required, and made seminal contributions. Okay, so from the humble beginning, like you can see here, that the part of the rockets are being carried very, very early. These are very well-known, famous photos. And this is the Tumba equatorial rocket launching session. So in 1962, actually the National Space Science Committee, that is Indian National Committee for Space Research, was formulated. And on 15th August 1969, ISRO started its journey. So ISRO has launched many spacecraft missions. They have tremendous applications. 91 launch missions. We are also self-sufficient in terms of launch vehicles. We keep doing amazing things in it. What interests me a lot also is the student satellites and the re-entry mission. And the last part, that ISRO has also launched a large number of foreign satellites for a large number of countries. Just a glimpse of a few of our satellites. This was the Aryabhata, the early on, Kalpana, Bhaskar. Then this is the student satellite, Swayam, which was made by the students from Pune. Let me come to the societal application. So if we look at what are the societal needs, we can think of water, food, housing, air, of course, environment, and good health. These would be the basic needs. And in addition, security, livelihood, safety, networking, communication, transport, education. These are the additional needs of a developed society. So literally, I will be able to take you through a very short, brief journey where I'll try to tell you how in each of this ISRO's technology, tools, approaches, different things developed by collaboration with the government agencies make a landmark contribution. Let's go ahead and look at some of these. So, very often, even when I have been working as an ISRO chair professor for a number of years, people ask what is the use of these satellites and rockets? Of course, these are amazing feats and they go in the earth, so they go in the space. But, there are different kinds of satellites, and I'm not going to go into details, but the remote sensing satellites, which are up to 36,000 kilometers up in the air, they are named as eyes in the sky. They go around in predictable orbits and they watch and observe amazing things that are happening around in the environment and on Earth. So for example, this is like a map of a town. These are glaciers. I mean, imagine mapping entire glacier map of Himalaya. It would be so difficult if one had to go and do it other than the space agency. Satellite applications, provide us with real-time images. I've got a glimpse here of the Holkar Stadium of Indore. This is taken from the space and reconstructed and taken. And this data can be compiled and put to use to study atmosphere, earth, landscapes, ocean, and lots of other dynamics. So some of the glimpse of applications would be urban and rural planning, agriculture and forestry, which is green economy, ecosystems, soil quality, rainfall prediction, weather, meteorology, and fisheries, agriculture, so many other things, So there are other kinds of satellites which are involved in communication. Time doesn't permit me to go into technical details, but these satellites, they have a battery of number of satellites which coordinate, and they help in providing services like the television depends on the satellite. We know that very well. Telecommunication, radio networking, DTH and TV operators use these bands, BSNL, Doordarshan, radio, strategic government uses security and safety, so many other things. So these navigation satellites, what do they do? So because they can map and track a large number of things. So what happens actually, the sensors and the other tools on the satellite collect this data and they coordinate with the Earth centers, which are our amazing capabilities with our ISRO scientists. Hats off to them for the technology tools and the development of all these, nice applications. So navigation and safety, roadways, then scientific research of atmospheric studies, resource measurement, location-based survey. Some of the applications of remote sensing and others are also vehicle tracking, fleet management, disaster management. You can see here that this is a satellite image, but this pollution that is happening here along the coast is tracked. And sometimes you can also find out what is polluting it based on the multispectral and other spectral images. And here you can see there are different pictures which tell you about the chemical composition with the distances and so many things. So, fisheries, mining, terrestrial navigation, and, NAVIC and other programs. So let's come to something which is very important and which is close to heart and essential, which is agriculture, food and other agriculture. So, in agriculture, it's a primary livelihood in our country for 58% of the population, but from land monitoring all the way to actually visualizing, quantitating and finding data about what is being grown, how much is the, produced this year, predicting it, rainfall, soil mapping, all of these can be complemented, used together. And since we are at USA, 85% of rural women are working in agriculture. So this technology touches our life in a very major way. There is this Mahalanobis National Crop Forecast Center, which is under ICAR, but collaborates very closely with SAC and NRSC and many other ISRO centers. And they actually look at crop protection, production forecasting, drought assessment, countrywide agricultural land use mapping. You know what? Because the satellite images are available over the years, one can look back what may have been the situation 20 years ago, today, and even through some modeling predict what might be the situation in future. So isn't this amazing that if one can do the countrywide land use mapping? And you know, the Bima Yojana, the Fasal Bima Yojana also makes use of this technology to, you know, estimate and provide guidance and compute certain things. So a horticultural crop inventory is possible. You will be interested because methane is very important. So methane emission inventory and carbon accounting can also be carried out using this satellite technology. Little bit more about this agriculture. ISRO has a very nice program called Fasal. And this Fasal is a crop forecasting approach, and it allows one to do a whole lot of different things like pre-season, mid-season, and then you can keep periodically revising it. So land use, soil quality, forestry, environment, biodiversity, all of these you can find in roads, and these are being done today. I know you will ask that why are there still disasters? Why are there still problems? So this technology is available. It's an enabling technology, but needs to be put with partnership with a large number of agencies more effectively. Now, there is also management support system. You know what? There is another program. I like the names which ISRO scientists and people have coined. They call it Chaman. And what is Chaman? It's coordinated horticulture assessment using management and geoinformatics. So, and we have today scientists from ISRO amidst us. So this is just a glimpse of, crop mapping, that is our fields. And you can even go deep in larger depth. You can have quantitative analysis. You can have spectral analysis. All of this from the observations made by our satellites and by communicating with the centers, and a whole lot of data processing, data analysis, geoinformatics, and so on. So this is the land use orchards. You can see this is the map of Nashik, which is grapes and pomegranate. Yes, please. Yes, please.
You have 3 more minutes. How many more
My
slides?
God. Okay, I'll go very fast. I have a few slides. Let me go very fast.
Yeah.
So this is about crop yellow rust and crop diseases. I wanted to touch upon this a little longer. Hyderabad National, INCOIS and in collaboration with ISRO, fish forecasting is done, like where and how the fisherman, when he goes for fishing, will find the fishes at which place they should go. And in fact, these fishermen are provided with location-specific information, ocean state forecasting, high wave alert, tsunami, and so on. Now, there is this ISRO's platform called Bhuvan, and this Bhuvan provides, again, a whole lot of geo technologies. This is the map of Bombay and a lot of data for government use and land use. Gagan is another program, another ISRO and Airport Authorities of India. Every second, if we are at a Bombay or Delhi airport, some flights are taking off and they are coming back. I always wonder. But programs like this ensure air safety operations. We have water body resources, groundwater, field water, rivers. These are all being mapped. And this information is freely available to anybody who wants to use. ISRO has Bhuvan and other platforms. I don't have time to go into it. So you can see that, Tungabhadra and Brahmaputra, this can be mapped, but you can see in the remote areas of Himalaya, also one can get rivers and water bodies and other maps and changes in snow caps and water bodies. Now, telemedicine is very critical and important. We all know that it's being used heavily. It's more important in remote areas or far off villages where through communication, medical help can be made available. Geoinformatics and remote sensing is very important in air pollution determination, environmental pollution, and so on. So forests have been mapped, a lot of forest. So this is very easy for me to state. A lot of applications have been put and large number of studies have been carried out to do this validation. So forest and biomass mapping, carbon credits, mangroves, glaciers, land degradation, all of these can be mapped. And forest fires are being mapped routinely. So this is a map of vegetation, and this is the forest cover in India. This is a map. You can keep seeing what has happened earlier, what is happening just now all over the country. And you can see these are forest fires here. And flood, cyclone, we know we can manage it much better today. So these are our launching vehicles. And just a glimpse of some of the interesting things, like there have been stamps which have been released over time. These notes also have satellite pictures. I have many things to add, but I'm going to cut everything short since I don't have time. These are some of the visionaries who have made remarkable contributions. And of course, this is Vikram Sarabhai, Homi Baba. We know, everybody knows Abdul Kalam, Satish Dhawan. I was very fortunate to have very close association with him in IISc. Dr. Gowarikar, who was also our Vice Chancellor. And, because there was some talk of water, the picture of water on moon is credited to our Chandrayaan-1 mission. And yeah, so that brings me to my last slide. So I'm reminded here of Ivalese Ropa Laviele Dwari, Tayacha Velu Gela Gagana Velu. So I would say that, we keep saying that things don't work, things don't happen. But when I look at ISRO, and I had a very close opportunity, and I was very fortunate to closely associated with Space Application Center, its scientists, and many other people working in ISRO, and also in Pune, and also in our space technology cell. I was impressed that thousands of scientists, technologists, and people whose names we never come to know have toiled and worked behind the scenes with commitment and in mission mode. And this is why we have such amazing success. You know that ISRO has also generated a lot of funds from the foreign satellite launches. It has also come up with an industrial or rather a commercial, arm. And I would say that self-reliance in space mission is something we are extremely proud of. And I would just end by saying that excellence is a continuous process and it doesn't happen by accident. So this is from our AstroSat images, although it doesn't have societal applications. It's very interesting that even India has a satellite up in the sky and which keeps looking at beyond, not as much as the, what we heard. And this is one small film that was made by Educational Media Research Center, which is hosted by our Pune University website. Thank you so much.
Thank you, Dr. Deepti. I think she gave a very good overview about space application, satellite technology applications, ranging from agriculture to even navigation and even railways, fisheries, about everything. She gave an overview about it. I will ask audience to any questions.
She's an old friend. Hi, Deepti.
Hi.
How are you?
Hi, Bhaktawar. How are you?
Fine, thank you. Deepti, as usual, you are doing just excellent work and my best wishes to you. Okay, since we are on an IWSA platform, and I have seen you on our platform at least 3 times, right? I have a suggestion.
Sure.
And this suggestion is spatially in view of the fact I recall reading very recently a statement by the head of ISRO, the large amounts of data which are being generated by our satellites, very small percentage is being used in India. So my suggestion is, you as a leader and a member of IWSA, yes, please, why don't, it's not very difficult, you can do it. Why don't you organize some sort of a workshop at your end or perhaps in Mumbai, as in per your convenience, for all the members of IWSA so that we in our small spaces can make use of this technology. Just think about it.
So when I was in ISRO, I will certainly think about it and would love to contribute. When I was, in university, we ran several workshops for our university people, and also I went and talked a lot in society. But my promise, I will do it.
Yeah, definitely. I'll get in touch with you in future.
Sure.
Okay. Thank you. Good luck.
Thank you. There seem to be some questions. Should I answer them?
Aja.
What is crop mapping exactly and how it helps to avoid drought? So I would say that these are two separate things. Crop mapping is from the satellite up to few meters resolution. We can get a complete idea. There are many techniques like vegetation index calculation. You can see the areas which are urban. You can see the areas which are rural. You can see, go back in time in terms of last few years or last few months and map how that field has been sown, what is its condition. It's possible to do soil mapping, water mapping. So all this put together in a coordinated way, yes, that helps. So crop mapping actually allows you to find out where are the fields and how much, let's say in January, what was their condition, March, what was their condition, today, what is the condition, and through very nice bioinformatics and other tools, you can predict what may be happening in future by using artificial intelligence and very high throughput technologies. And so this would be crop mapping. And drought is something related, but very important because ISRO's technology allows us to look at the groundwater, we can look at the rivers, we can look at the water in many different ways, quantitated. So predictions become possible, and the rain predictions, monsoon predictions, etc. We have MOSTAC, which SAC has, and I didn't have time. There is Vedas, which is also another tool which allows you to even use it on your mobile to map the fields and other things, So yeah, I hope I have answered your question.
Hello, Deepti madam. Good evening.
Yes, good evening.
Niranjana from Kolhapur.
Sure.
I would like to ask you one question related to mud flats, related to mangroves. So we have done one mapping from mapping of Thana Creek.
Yeah.
So there were no correct estimations related to which we have satellite data, static mapper. So I would like to ask you, which will be the best satellite data to map the mud flats and mangroves?
So I will look up something and tell you offhand because we have so much of tools and technology. So Bhuvan has a lot of tools which are very user friendly and they would help you with the mapping. I will tell you what I have done with the mangroves. We have looked at the microbial biodiversity, but yes, you are absolutely right. I'll communicate with you and let you know, and I'll put you in touch with people who can help you with the accurate mapping, if that's fine with you.
You can send your answers to her. Time is limited.
Yes, thank you, madam. Thank you.
One more.
Yeah, Niranjana, I'll let you know. Yeah.
For your wonderful lecture. And actually, I wanted to tell you, it is not underutilized. Many places utilize this data, and you can see that nowadays in train you get when the train is will be arriving at, you will get the status, live status. That also, even agriculture, only thing some of the farmers, they are not aware of it. It is data is being used, and she is the.
So I totally agree with you, ma'am. If I tended to give the impression that it's not used, I'm sorry about it. It's used extensively. I just meant that state governments and NGOs and universities, etc., should get into it and use it much more and make it help to spread it and make it more user friendly for common man. That's what I meant. I agree with you totally, and that's what I'm also saying, that it's amazing what is done and it's used extensively. Sure.
But one point at the forum I would like to mention is, now it is a data democracy what ISRO believes in. So the recent remote sensing data policy and the geospatial policy say that all data is going to be free to the public. So already there are many applications, ma'am, almost all are being used on the ground, as very little is known to the common public, especially the woman.
That's what I meant.
Using, as you have seen, I have asked her the question, one of the interpreters, she told that she has been using it.
Sure.
So they are being used, and now with the data democracy, more and more applications will be coming into the future.
Thank you. I would like to thank both of you and Ibza for giving me this opportunity to share a few of my points with you. Thank you very much.
Thank you very much, ma'am.
Thank you. Next speaker is Ritu Karidhal. I am very happy to introduce Ritu because she is not only my colleague and she is my friend also. And she is a senior scientist in Indian Space Research Organization, and she played a key role in Mars orbit mission. She was also the mission director of Chandrayaan-2. Now I think Chandrayaan-3 also she is mission director, is not reflected here, which is a very, very challenging mission. Chandrayaan-3 is going to be a very, very challenging mission because of the lander. And coming to her qualification, she has done MSc Physics from Lucknow University, and she has done MTech from Indian Institute of Science, Bangalore. And she joined ISRO in 1997, and she has worked for many prestigious missions of ISRO. And she has handled responsible position for many missions. And she is the Deputy Project Director for Mars Orbit mission. And she has published nearly 22 papers, both in international and national publications. Her list also is very big, so I'll make it precise. She has got ASI Team Award and ISRO Team Award for Mars Orbit mission in 2015. And she got Women Achievers in Aerospace 2017 by Society of Indian Aerospace Technologies and Industries, and the Baroda Sun Achievement Award by Bank of Baroda. And she was a member of Gender Equality Advisory Council of G7 and UK Presidency in year 2021. And currently she is holding the responsibility of Group Director of Mission Planning and Operations Group. She has received honorary doctorate degree from UP Governor Mrs. Anandiben Patel at Lucknow University, Lucknow, and also ISA Luminous Award 2019 at Bangalore. Now over to Ritu. She'll be talking about challenges about Mars orbit mission. Now she will take from Earth to other planet. Okay.
Good evening, everyone. Good evening, madam. Am I audible?
Very much.
Yeah. First, let me thank IWSA for giving me this opportunity to come at this platform, and I'm very happy to see my senior eminent scientist, Ms. Dakshani, madam. So what madam told, I will be just covering. And that this is the last lecture talk, so I should not take much of the time. So I will be covering the challenges and the accomplishments of Mars orbiter mission. My slides, I think I'm able to share. Yeah. So as we know, this Mars orbiter mission, this was first Indian interplanetary mission, which is going to go beyond Earth's regime. Before that, we have had multiple missions, and then one of the important mission we had at that time was Chandrayaan-1, the mission to Moon, and it's really the Chandrayaan-1 mission was the mission which really gave the evidence of the presence of water as a on the polar poles of the moon, on the south pole and the north pole of the moon. And after that, our next challenging mission was going beyond Earth's regime and go towards Mars. That is our next neighbor, Mars. So this mission being the first mission, our mission objectives, when we start a mission, we have a mission objective. So our technological objectives were the major objective, where we had to design and realize the spacecraft with having the capability to survive in the deep space, and get captured in Mars orbit. This first time, this something of this sort we had to do. And yes, once we reach around Mars, when we are in the orbit of Mars, we have had to have some scientific objectives also, where we can explore the Martian surface, the morphology, mineralogy, and the Martian atmosphere by the indigenous scientific instruments. But then the making of MOM, one of the toughest challenges which we had at that time is completing this project in just 18 months of time, with no previous heritage of interplanetary mission. The difference between our earthbound mission and the interplanetary mission is when we go deep into the space, the signal, to and fro time of the signal, or what we call the round trip time, is like of the order of, it can go up to 40 minutes. Such a huge time delay. Any micromanagement, actually speaking, when we talk of, Madam has given a previous presentation of the payloads and all the Earth observing satellites. There all the satellites which are revolving around Earth, we are able to send the signal anytime, get the data, and then any contingency, any anomaly happens, we can do the micromanagement, we can attempt to the, any recovery of the, any anomalous situation. But then when we go in deep into the mission, this micromanagement is not possible. So what it meant that we had to build an extensive amount of onboard autonomy. We had to build the systems which were capable of doing self-diagnostics, the self-recovery, as well as, executing all the instructions with the highest precision. Because, the minutest error in doing all those instructions, executing those instructions, would again jeopardize the whole mission. Actually, that is what has happened at that time to many earlier missions of NASA, Russia, Japan, or China. Out of 51 missions that time so far, only 21 have succeeded, and then the success rate less than 50%. And then no one could achieve it at the first time. So, we started working on it while the hardware part that we used was adapted from previously successful missions. The autonomy software, which I'm talking about, it was almost a new venture, totally a new venture for us. And, I'm very happy to share with you that, when we started working on the onboard autonomy, we had to have at that time, a rigorous process of, brainstorming sessions with all engineers in all areas, be it mechanical, electrical, electronics. But it is very, I'm very happy to say that, at that time, I can say equal participation of women and men scientists in this project. Of any area you take, maybe even I'm very, proud to say the flight dynamics, our leader, madam, is sitting here. She was leading at that time. So similarly, in any area, you say mechanical or any other area, electrical, electronics, women scientists were playing a very important role at that time. And so we used to have a lot of brainstorming sessions, and with that, a network of autonomy was drafted with the different levels of fault detection, recovery. Thousands of lines of codes, new codes were implemented on onboard computers, followed by extensive reviews, testing, and all this in just 10 months of time. Something which looked very much impossible at beginning, but yet could be achieved in that record time. And yes, being one of the prime designer of this MOM autonomy, I remember I used to spend many nights, late hours spending with the team and working on the design draft, all those aspects. But yes, at the end, we could achieve in the 10 months of time, everything was ready and could be implemented on the computers, onboard computers. Next, coming after they're talking about the software, the autonomy part, let us come to some of the few hardware parts which really were challenging for us. One is the propulsion system. Propulsion system is a system, that is where we use the liquid engines. Those engines only we adapted. Actually, they were used earlier also in geosynchronous communication satellite, but then what was new for this? This was like the engines, they have to work is something like, when we had only one engine, and that same engine had to work in the earthbound orbit, and also after traveling for 10 months of time, same engine had to be reignited once we reach the Martian orbit. This is something totally new because, it's like a car which is not started for a long time, and this always gives uncertainty whether it will start or, when you restart it, whether it will start or not. The same sort of limitations or problems were expected, but then the engines were perfected. There was a deep space environment, and extensive testing was done. And then and then we can say, we had a test firing also in orbit just before getting acquired by Mars planet. We had a test firing, and it really worked very well. So this was the propulsion system. Coming to next, very important, the communication system. It's like an antenna, they are the important part of the full spacecraft, because they work like a ear of the spacecraft. We had three antennas, three different types of antennas. And the main antenna, which was a high gain antenna, we can see, something like when you send a signal and it has to come back to you, it is not the distance of 36,000 kilometers when we talk of geosynchronous orbit, where we had, or maybe it's, let's say 3.8 lakhs or 4 lakhs distance of moon. But this antenna had to respond to the distance of around 400 millions of kilometers. Its sensitivity is so, we had to tune the sensitivity to so that it responds at that distance. It is like, task of hearing a person's whisper across the soccer field. But yes, this antenna also worked very well in all phases of mission, whether it's 200 millions of kilometers or the farthest distance of 400 millions, it has really worked very well. Coming to the next important system, which was a power subsystem, like this is an important aspect of any mission, because this is the system which generates. Basically, it is a solar panels. We have solar cells mounted on the panels. These cells only generate the power. And but what was the challenge? This happens for any spacecraft. But what was the challenge is, we had to have the panels which are generating power even when we are in the Earth's orbit. But then when we reach to the Martian orbit, where the solar power, the intensity reduces by half, by factor of around 1/3, that time also it has to support the power generation. So this like tuning the panels, tuning the efficiency of the cells, which can work even with the high intensity and with the low intensity of sun, of the solar power. So this is the areas were designed, and even the temperatures also, they had to undergo temperatures of around, during eclipse, it was predicted that in Martian orbit, the temperature can go as low as -185 degrees centigrade. So even those temperatures also, the cells have to retain their efficiency. So it was designed to work, and it also really worked as per its expected expectation. Now, the next important thing, the most important part is, for any interplanetary mission, is to design a precise path, a trajectory which can take the spacecraft from Earth to Mars. But then we had the limitation of we should do everything with minimum fuel, So this you can see that when we talk of our earthbound satellites, we have only Earth and the satellite. It's a two body problem. But when we talk of interplanetary mission and getting captured by Mars or so
You are left with 5 minutes.
Yeah, yes, madam. So I'll just finish. So this is like, it's a 4-body problem, and then we had the first time we had to design this path, the trajectory which will take us near to Mars, and then we can get acquired by Mars. But then another obstacle we had to overcome is also the launch window, the time of launch. For Martian orbit, anything, it comes like the opportunity is not like every month or every day. It comes once in 26 months. Because there's a particular geometry which is formed between Earth and Mars, which provides an opportunity to launch with minimum fuel. So, we had to realize everything with this short span of time. And then everything was, completed, and in time we completed, and the satellite was mated with the rocket. Everything was ready in time. But yes, another important part which I want to cover is to further minimize, the fuel requirement. It was like planned that when the PSLV rocket, when it takes off, and when it injects the satellite, it basically, when it takes off from somewhere, you can see here, from our Sriharikota, it should not inject over Mauritius or Biak, but it had to inject somewhere over the Pacific Oceans. And there we did not have any antennas or ground stations to track the launch vehicle on the sea. So we decided to deploy the 2 ships over the locations, which would take 2 months of time to reach there. But then what happened? The ships could not reach on the expected dates due to bad weather conditions. There was a huge storm over the sea. They got delayed by 10 days. We were really racing against the time. But before the time was up, on 5th of November 2013, our mighty PSLV took off and put the spacecraft in its first parking orbit. And this is one, as I mentioned, this most unique part of the Mars orbiter mission was the trajectory, having this, you can say, multiple slingshots. With each sling shot, the distance from the Earth increases. And then 25 days later, we have the final maneuver, which we call, trans-Mars injection. And the spacecraft had to leave the gravity well of Earth and move towards Mars, which we call basically cruising. The cruise direction, the importance is the cruise. When we leave, the direction of the cruise is very important. It needs exact and accurate performance of around 99.9%. Actually speaking, many other missions had failed either before leaving or just while leaving the Earth's gravity. But ISRO, we can say, made history on 30th November itself when the MOM successfully left for the cruise in its first attempt. To show you the importance of this, how important it is to achieve a cruise direction is like, you assume like we have a golf, just go right outside right now and hit a golf ball towards a hole somewhere located in the Los Angeles. The golf ball has to go straight into the hole. And, to make it even more challenging, the hole is moving. I'm not sure whether it will play that, but yes, it has to go straight into the hole. That was the challenge which we had to really achieve in terms of direction of the cruise. Yes, the D-Day arrived, and being the Deputy Operations Director, actually this full distance of full duration of cruise was around 10 months of time, 600 millions of kilometers of distance it traveled. We were just very near to the Martian surface, around some 500 kilometers away. And being the Deputy Operations Director, my team was responsible in ensuring that this all operation takes place as per the set configuration. Because again, as I told, the minutest error in the operation would jeopardize the whole mission. The D-Day, I remember still, 24th September 2014, morning 7 a.m. IST. We received the first signal, from spacecraft indicating the correct start of the auto sequence of the onboard computer, and everything, 21 minutes later, we saw the main engine, it started firing. That was the time we can say that, yes, when the engines are firing, our half of the success was ensured. But then 4 minutes later, what happened? The data, all the signals stopped coming. What happened? Actually, the spacecraft went behind the Mars. If no signal can reach, like as if, for us, time had stopped, all the eyes in the control center, it was remaining glued to the computer screens. For 26 minutes, there was a complete and utter silence. But then at 8 a.m. IST, the history was made. And then this pictures, we can say the contribution of all women and men scientists, and mainly I want to really very proud to say that women scientists really played a very important role in this whole mission. And this full hall, we can say at that time, erupted with jubilant cheers and claps. I could not believe, I had become part of such an important moment. Yes, Mars MOM entered successfully into Martian orbit with many first into its account. It was the first mission to succeed in its first attempt. It was the most economical project, interplanetary mission. And then it was a project realized in the shortest time of 18 months. It was the first Indian satellite having full-scale onboard autonomy, and yes, the youngest team with equal participation from women and men scientists. Today, I can say, it has Mars orbiter mission has sent almost huge amount of payload data we have received. There's a few of the science things, the image of full Martian disk, the wells of Mariner, a large Martian crater, and like that, full Mars atlas could be prepared. I feel the most important contribution is like this mission has created a huge inspiration and motivation among the girls and the women across the nation. It has set an example of how to include, inspire, innovate, and move towards a better world of equality, and show to the whole world that we are second to none. Thank you very much.
Thank you, Ritu.
Thank you.
For the wonderful lecture about the challenging mission of Mars orbiter mission. I think because lack of time,
Yes.
not asking audience to ask you any questions, but they can send the mail to her. It will be there with them. Okay. Any questions? They will send you the mail.
Yes, madam. Yes, madam. Sure, sure. Yes.
Thank you. Thank you, Ritu. Thank you all for all the wonderful sessions, 3 sessions we had. I will not talk much more because already it is delayed. You have heard about all the speakers. Thank you all.
Thank you. And let me thank to IWSA and everyone for giving me this opportunity. Thank you.